Hello and welcome to another video. Today we're going to be covering the change of parameters on a sphere theorem. So, this time we're going to be working with two charts. So let phi of u as a subset of the k-dimensional real space be a map mapping this subset onto some surface S, and xi be likewise some k-chart mapping some subset of the k-dimensional real space onto the surface S, be two k-charts of the k-surface S such that M, which we define as the intersection of phi of u and xi of v, is non-zero. So in other words, we have our surface S over here. It's better. Something like this. And we have our two charts over here mapping some spaces u and v onto parts of the surface S, right? And their intersection is non-trivial. It contains some elements, and we call this intersection, which both of the charts map, M. Now, finally, we get to the claim. So then the map, and it is xi inverse composed with phi, which maps phi inverse of M. Which maps phi inverse of M, obviously, to xi inverse of M by construction. And then this map is a diffeomorphism. In particular, it is smooth. Right. Moreover, it holds that D, or the Jacobian, of the composition of functions xi inverse and phi is equal to, and I will explain this notation in a second, the Jacobian of xi at v composed with the Jacobian of phi, right? Oh, and I forgot the argument on the right hand side, of course, of u, right? Okay. The nature of v is obvious from the construction. Now, or even more plainly, we shall use the sets. That will make it more obvious. Now, the important thing to notice here is the notation here. Basically, this means, the lowercase d means that it is still a Jacobian, as if it were a capital D, but it is isomorphic, right? So this denotes an isomorphic Jacobian. In other words, the matrix representing the Jacobian is a non-singular square matrix. Okay, now, how do we prove this? Proof. The proof is simple. It's more of an exercise, really. So we have x is equal to phi of some u is equal to xi of some v, which is an element of M, for u is an element of u and v is an element of capital V, right? Now, we also define pi as the projection which projects the n-dimensional real space onto the tangent space of S at x, right? So tan x at S, right? And it is easy to see it is an orthogonal projection. Now, we finally define G as the composition of pi and phi, right? And h, which we define as the composition of pi and xi, right? Now it is easy to see that all of these are smooth. Pi is smooth because it is a projection, that's obvious. Now G is smooth because phi is a smooth map, and it is composed with another smooth map, and likewise for H. So all of these are smooth maps, which will prove handy in a second. Now, we can write, or we know that the Jacobian of G at U and the Jacobian of H at V are non-singular. We know this because the Jacobian of phi and xi are both non-singular by definition, right? And we compose it with pi, which is a simple projection, so nothing can go wrong here. It preserves smoothness. So, or rather, non-singularity of the matrix. Essentially, if we now have, if this was represented by a rectangular matrix, this will simply make it a square matrix, right? And if the rectangular matrix had all the columns linearly independent, then if we remove some of the columns, they will still be linearly independent. So this is fine, and we know that these maps are non-singular. Thus we have, by the local diffeomorphism theorem, we have that GH are smooth, obviously, diffeomorphisms on some neighborhoods of the points UV. And thus, finally, thus, H inverse composed with G is equal to phi inverse composed with phi. The revelation being that everything is invertible without any problems, because diffeomorphism is not only invertible, it is smoothly invertible. So we can write this without any problems or fear of them. And we know that these not only are well defined, but these are also diffeomorphisms. By definition of a diffeomorphism, its inverse is also a diffeomorphism. And if we compose them, then the diffeomorphism property is retained on the neighborhoods. Well, on these neighborhoods. Now, phi is equal to xi composed with xi inverse composed with phi. We can do this because composition is associative. Now, this implies to us that also that Jacobians behave this way. So we have the Jacobian of phi at U is equal to the Jacobian of xi at V, composed with the Jacobian of xi inverse, composed with phi at U. And now we talked about xi and phi being, well, if this holds for the Jacobians, it also must hold for the isomorphisms from the k-dimensional real space into the tangent space, right? And now simple algebraic manipulation of this yields the formula. So we have d phi of u composed, you have the inverse d xi v inverse composed with the d phi u is equal to the Jacobian of xi inverse composed with phi at u. And this concludes the proof.